Alright, so last time we made a rectangle, we've made a smiley face, we've made circles, and before we start digging into making something really cool, I thought maybe we should talk a little bit more about the different ways we can deform an object once we've made it. Because we have a rectangle, but we can do a lot with that rectangle by deforming it. So so let's just continue where we left off and see what we can make by changing some of the parameters. So like the main parameter that goes into everything thus far has been the UV coordinate, and we can play around with the UV coordinate to change the shape of this. So one simple one is what we've seen before is, okay, you can multiply the UV coordinate by some number and it will do a uniform scale on the object. Similarly, we can just do this on one of the axes to just scale one of the axes, right? So if I wanted to, let's say, have my rectangle be completely squashed, I could multiply this by some large number and it will squash my rectangle. Okay, well, that's not like super exciting, so so let's do something more with the UVs. And before I do that, let's just split them out into an X and a Y, then that way I don't have to type uv.x and uv.y each time. So I just do it once. uv.x and float y equals uv.y. And then over here, I have to pipe in my new UV coordinates, and I have to pack them back together into a vector 2, so x dot y. All right, so this shouldn't, or this should just be my original shape, and it is. All right. So one thing we could do is we could make it that for every, let's say, for every horizontal line in the image, it shifts the box a little bit to the left or to the right. And so if I do that, so let's say, well, if I shift all of the lines, right, so I could just do x plus equals 0.2, let's say, that will just move the box. Okay, because the 0.2 is constant, right? It doesn't matter how high you, like which pixel you are, it will always add 0.2. But if we make that a function of the y, then we can skew the box. So if I do this, it will deform the box like this, and you can change the effect by multiplying this by some number. So you can, if I multiply this obviously by 0, then it will cancel the effect. If I multiply it by some smaller value, it will attenuate the effect. And I can also make it go the other way by just multiplying it by, well, I can put the negative over here. It's multiplying by a negative number. Okay. Similarly, so this is a way to skew the box. Similarly, what we could do is, if I go back to my original box, we could screw around with the parameters of the rectangle. If you remember from last time, this is the left side of the rectangle, the right side, the top and the bottom. So if I start screwing around with, let's say, the left side, so I could go here and say plus y, and I will attenuate it right away so that it's not such a large effect. And now you see that I'll just change one of the sides. And you could do this with all the sides. So if I want to make this box tapered, I could do this, and here I do minus y times 0.2 or 0.3 or whatever I want. So now I have a tapered box. Okay, I can make an uneven tapered box by changing the value there. So you can see that by kind of screwing around with these values, and oftentimes you kind of have to just try and then see what happens, and then discover things that you're like, oh, I can use that for something. So yeah, so that's quite powerful. So let's see what else we could do. Let's say I will add, let's say I want to add the y, but not in the normal tapered way that we had, but I'm going to, actually, let's make it horizontal because it's easier to understand. So let me change the shape of the box to be more of a horizontal line. So I'm just going to go from -0.5 to 0.5, and I'm going to make it nice and thin. All right. And then what I can do is, let's say I wanted the boxes to start over here, and then it bends up, and then it comes back down over here. So, well, what I would have to do then is I'd have to have some magic number, let's call it m, that is 0 where x is -0.5, right? X is -0.5. It's also 0 where x is 0.5, but where x is 0, where x is somewhere in the middle, it's some higher value. Okay, and for that I can use just a simple parabola. So if I just went to Desmos, which is I have opened in a different tab, which is a great graphing calculator that helps you a lot with coming up with the right functions for things. So if we just channel some high school lesson here, so this is a standard parabola, and I want it to be, I want it to go through 0 at -0.5 and 0.5. So if you remember how that was done, you do x minus 0.5 times x plus 0.5. Now I have a parabola that goes through 0 at -0.5 and plus 0.5, and maybe I want to turn that thing around because I wanted it to go up instead of down. So now I could just take this exact formula and put that in here. So for my m value, right? So for my magic value, so I'm just going to go here and make my magic value, both m equals x minus 0.5 times x plus 0.5. Okay, let's just see what that does. Well, great. So yeah, and any kind of function that I want here, I can just plug in and it will make that shape. So if I wanted to say I wanted like I'm kind of happy with the way it goes up, but like I wanted to not, like I wanted to start at 0 and then kind of go up like that, like a smooth step would. So I can, well, I could call this function something here, a, and now I could say b equals a times a. So now you have a function that, because if you multiply a function by itself, everywhere the function crossed 0 before, now it has a derivative of 0, meaning that it's flat. So, and then I need to multiply it by some value to make it like push up a little bit higher. So I could say times 4. Ah, perfect. All right, so we'll go back here. So I could say here m equals m times 4. And why did it turn around? Let me see here. Oh, this is already negative. Okay, hang on a second. I need to turn this around here. I need to turn it around here, because this was already negative, and if you multiply a negative number by itself, it becomes positive. So that's why it flipped around. So this should fix it. There you go. And again, I mean, we already kind of showed it here. Like you can attenuate this, so you can make this times a smaller number, and it will go. It will become smaller. The effect. All right. So now this one in particular here, this almost looks like a sine function. So you can also do this with the sine function. So let's do it. So let's say I can get rid of all of this. I can just say sine x, and let's see what that does. Okay, that makes a straight line. That kind of seems weird, but it's not weird, because if I go here and if I show you what a sine looks like on that same interval, you will see it looks like a straight line. It's just that you have to zoom out in order to see this. So what we have to do in order for this to be more interesting is we have to squeeze the sine. So the way to squeeze it is by multiplying it by some larger number here. Oh, I keep putting a decimal dot because ShaderToy requires it. Alright, so let's just see what happens if I do that. So I do sine times times some value, and that's going to be too large. Yes, and we're going to have to attenuate it. So I can do times .1, and now I have a sine. And now maybe it would be nice to make this sine move. So up till now we've only used, the only input to our shader has only ever been the position on the screen, right? The position on the screen comes from this UV, which comes from these inputs here. So we can add another input, and so just like we have frag chord here and eye resolution, so that's ShaderToy kind of gives you that. There's another thing that ShaderToy gives you, which is eye global time. It's called eye global time, and that's this value right here. And you see that, like, if you press pause it stops, but if you press play it increases. It's the number of seconds since you started, since you last reset or reload the page and press play. So because this is a long name, I usually like to call that just t. So I do float t equals eye global time, and now I can put this in here. And now if I make my magic value here just a function of t, well, now my wave will disappear and I will just have a straight bar that will go up and down. Okay, because for every x it's the same. So you have to have both t and x. So x plus x times 8, let's say. And now we have a wavy line, yay! All right, so what else can we do? Well, one thing we can do here that we kind of never really used is this blur value here. So if you remember for the rect function and for the circle function as well, we always had a blur value here that that kind of dictates how wide our smooth step is on either side of the band. So we could play with that. So we could say, because we've always had it quite sharp, but we can make it more blurry, and you could use that for something else in your image. So now let's see if we can vary this blur value from the left side of the snake, let's call it, to the right side of the snake. So let's say on the right side of the snake I want it to be, let's say this, and on the left side of the snake I want it to be this. So how would I do that? Well, the first thing I would do is I would take this here and I would call this blur, because I'm going to make that a variable that I'm going to build. So call it blur here. And now, so basically we need, and what, so the blur is a function of what? Well, it's a function of the x position, right, on the screen. So we have to make some sort of some function that takes an x as an input and it makes a blur as an output. And so the blur that we want as an output is either 0.01 on the one side, right, or it's 0.2 on the other side. So what we need is a function that remaps, -0.5 to one of these numbers and 0.5 to the other. And what I like to do for that is I like to make a universal function for that. They can just remap numbers from one domain to another domain, which is really handy. You will use that a lot. So let's make that function. So I'm just going to go here. I'm going to call that function. It returns a number, so a float. I'm going to call that function remap, and the remap is going to take as an input two domains. Like so, the first one is a domain that goes from A to B. The second one is a domain that goes from C to D. And then we have our number that we want to remap, which is also a float. Okay. So if t equals A, then the output should be C. If t equals B, then the output should be D. If t is halfway between A and B, then the output should be halfway between C and D, and so on and so forth, right? So that's what we're trying to build here. So how do we do that? Well, the first thing that I would want to do is what I would call normalized value t. So, and by that I mean that I want a value between 0 and 1 for t. So like the first function that I'll make, and actually maybe I'll just write that out here. I'm going to make a simpler remap, which is a remap that only takes one domain, and actually it's called remap 0, 1. So this is a function that takes an A and a B and a t, and basically it returns, like if t equals A, then it returns 0. If t equals B, it returns 1. If t equals halfway between A and B, it returns 0.5, and so on and so forth. All right, so I'm going to return a number here that, well, let's look at the first point. Like if t equals A, I want it to return 0. Okay, well that is quite simple because I could just subtract A from t. Right, so now if t is A, then you get A minus A, which is 0. Great. And now, like the second part is I want to scale this t so that the distance between A and B equals 1, right? So that if it goes from A to B, t goes from 0 to 1. Well, the way to do that is just by dividing it by the range from A to B, and the way you do that is B minus A. So now you're dividing it. So now let's see. Okay, so if t equals A, then I get A minus A is 0 divided by B minus A, which is 0 divided by something, which is 0, which is what we want. If t equals B, then I get B minus A divided by B minus A, which is something divided by itself, which is 1. So that's great. So that's our the remap 0, 1 function. So now that we have the remap 0, 1, so I can do remap 0, 1, A, comma, B, comma, t. So now I have a value that goes from 0 to 1. And now I need to remap that into a value that goes from C to D. Okay, well, the way I do that is I have to do the inverse as what I did here, divided by the range. I have to multiply it by the range. So multiply it by the range, which is D minus C. And then here I subtracted the first number. Now I have to add that first number. So plus C. All right, and then I can just return this. All right, so let's go back down here. Okay, what were we doing again? We want something that is blurry on one side of the snake and it's not blurry on the other side of the snake. So so now we can use our remap function. So remap, and what do we want to remap? Well, what's our input? Our input is our x, which is in this domain, right? From minus 0.5 to 0.5. So I do minus 0.5, comma 0.5. And our output was the blur value that we want, which is a very small value on one side and a larger value on the other side. So the very small value was 0.01, and our large value is like, I don't know, 0.25, let's say. And now we need to plug our x into that. All right, so I'll go here, and I cross my fingers, hope this works. Oh yes, it works. Great. So now we have something that has 0 blur on one side, and it kind of progressively gets blurrier towards the other side. All right, so one last thing. Right now this gets blurrier in a linear fashion, meaning that the rate of it getting blurrier is kind of equal across the entire length of the snake. And sometimes you don't want that. Sometimes you want it to be not linear. So what you can do in that case is you can take your blur value and you can start multiplying it by itself. See what that does. Times equals blur. So now I have something that stays at a low blur for much longer, and then it goes larger. So yeah, that's something that you can play around with. So I could just do this, for instance, pow for power, and then, well, what I just did was the same as this, but now I can make this larger or smaller to kind of play around with it and see what I can do. So sometimes what you have to do in this case, because right now you don't see anything happening, is because the blur is already a very small value, and if you multiply it by itself, then it gets exponentially smaller, right? So sometimes you have to pre-multiply this to get this back into a range that works a little bit better. Okay, so now you can see that it stays at a low value for quite some time, and then it exponentially explodes into a larger value. So yeah, so that's another way to kind of massage the numbers in a way that will give you the result that you want. So I hope that helped somebody, and I hope to see you next time, and we'll make something really cool next time. So, ta-da.